Welcome back to Data Science for Everyone. This is video 4 if you're following along, and video 1 if you're new here. Welcome. Today we are going to be talking about something very important and something that I think too many of us gloss over, myself included, which is why causality is hard. We said in the last video, if you're watching in order, if not, don't worry about it. We said in the last video that causality is at the core of most things we want to understand with data. Why is this going up? Why is this going down? Is this going to go up? Well, asking is this going to go up means what has to happen for this to go up? So what causes that to go up? So we tend to ask a lot of causal questions. Not always, but we tend to ask a lot of causal questions when we work with data. So association is when two things go together. That's kind of it. If you've taken any kind of statistics before, you're familiar with the idea that association is not causation. If you have not taken stats before, don't worry. We're going to talk about it right this very second. And if you do think, oh, I know exactly why association doesn't equal causation, stick around. There might be some new reasons that maybe you haven't thought of or haven't thought of recently. Classic example of association, weight versus height. In this particular case, we have a positive association between X and Y. As height increases, weight increases, and vice versa. X is the height variable. If you're super brand new, the x-axis is the horizontal one. That's the x-axis is height. The vertical axis, Y, is weight. And we are plotting the weights and heights of individual people, or it could be weights and heights of other things, and comparing how they go together. And in this case, the higher the height, the higher the weight, and vice versa. So we'll talk more about correlation later on. Correlation is a specific, very common type of association, but we're not even going to get there. We're literally using what a colleague of mine calls the ocular method, which means looking at, to see, aha, as someone's weight goes up, someone else's height goes up. A negative correlation is when as X goes up, Y goes down, or vice versa. So they go in opposite directions. In this case, X is our absences from class and Y is our grades. This is just a correlation. And I think this is true in my course. I stopped taking attendance some time ago, but I'm reasonably sure this correlation holds in my courses as well. Notice, association does not have to be linear. That is to say, form a straight line like this negative correlation or the one we saw on the last slide, a positive correlation. Associations can take all kinds of different forms. Maybe as X increases, Y decreases, but then as X increases even more, Y increases. There could be no association between X and Y. We'll revisit this later on, but the assumption of linearity, the assumption that if there's a positive association, we tend to picture this scatter plot going up to the right, is not necessarily the only way that association can show up, but it is the one that we tend to assume when we talk about it. Establishing association is easy. I highly recommend you go to this website, tylervgen.com. Forgive me, Tyler, for saying your last name wrong, where he has built a service that generates spurious associations, meaning associations that we don't have any real reason to believe have any causal relationship, but if you plot them, look like they go together. So my personal favorite from his website, he has lots of really fun ones, many depressing ones, but still fun, is that the number of people who drowned by falling into a pool correlates with, or in this case, we can just say is associated with, films Nicolas Cage appeared in. Now, we're not getting hung up on the strength of the association, but if we just plot these two trends, we see that over time, the trend of, in red, number of people drowning by falling in a pool actually associates with films Nicolas Cage appeared in. Now, a causal story would say there's something about films Nick Cage is appearing in that's causing drowning, or that drowning causes Nick to do films. We could test it. This, it's a silly example, and it's sort of easy to see the ones that are associations that are spurious, but a lot of associations out there that we take very seriously may also be spurious. We just haven't tested them enough. So let's take this one seriously. Let's say, all right, my hypothesis, the rate of Cage films is associated with the rate of pool falling deaths. So my hypothesis is just about correlation. We see an association. Gosh, maybe there's something to my theory after all. We probe a little bit further. And if you watch the previous videos, you know that one way to probe further is to say, well, what's the mechanism, right? What's the mechanism by which Nick Cage movies are causing people to drown by falling into pools? Are people so excited about Nick Cage movies that they lose track of where they are and they fall in? Are they so devastated by the movies that they're throwing themselves in? And so on. So we haven't established any causality. Our ideas about causal mechanisms may give us an idea of where to look for more data to pursue this. But generally speaking, we all kind of know this is silly, or we think that even if there is a correlation, it's probably there because Nick Cage films tend to come out in the summer and people tend to swim in the summer. That's probably the story here. But that doesn't mean getting rid of Nick Cage films is going to save people from drowning. So it's an association, relatively easy to establish, very difficult to say much more causally with just this alone. And this is an example of where subject matter expertise comes in. Knowing more about the mechanisms behind drowning, knowing more about Nick Cage films could help us study this a little bit more closely if we think something's there. I already introduced this as something relatively silly. Please generate your own. It's very fun. Something like divorce rates in Kentucky are associated with high-speed rail crashes in North. It's amazing. All right. So why is establishing causality so hard? Let's get very specific about this. Well, the first big problem is it relies on something called counterfactual reasoning. Sometimes you'll hear this talked about as the fundamental challenge to causal inference. What I mean by that, okay, brace yourselves. This is in the weeds. Technically speaking, when we speak of causality, the causal effect of some factor X is the difference between what actually happened and what would have happened had X been different in some way. So the causal effect of Nick Cage causing people to drown is the difference between what actually happened, he starred in a movie that summer, and what would have happened had he not starred in a movie that summer. So it's what would have happened had X been different. We're going to get even more in the weeds. So the causal effect of treatment X. So we can talk about X as a treatment, right? People are being treated with this drug of Nick Cage movies, for example. The causal effect of treatment X on an outcome for a specific case at a specific time is the difference between the actual outcome and the hypothetical outcome that would have occurred at the same case at the same time had X not been present. Whew. Counterfactual basically means, zooming back out, counterfactual means counter to the fact. Showing causality is only possible if we can truly run the same history we saw again with only manipulating X. If I think a medication cures headaches, I need to be in the exact same conditions where I take the medication and see what happens to my headache, and I don't take the medication and I see what happens to my headache. That's actually impossible because, as far as I know, we haven't invented time travel, though my colleagues at the end of that futuristic hallway are working on it. So we have to do other things. With experiments, as you may be aware, with, say, a drug trial, we try to control everything except for this group gets the drugs and this group doesn't. We try to randomize so that people are roughly the same, or we're kind of erasing any meaningful differences between them that might be affecting the results. Still not perfect ever, but lots of times we can't even do an experiment. So we have to just look at data and be really, really thoughtful and careful about it. So really what we're doing, if we're claiming, oh, Trump caused the economy to go up, Biden caused the war in Ukraine, is we need to imagine what would have happened if something other than what happened. Remember when you came to data science thinking it was going to be mostly programming? Welcome to the deep philosophical pieces of data science. I love this part, right? Okay, so if X causes Y, we need to see what happens to Y in a case where X is not present, but everything else is exactly the same. So it's what if scenarios. So, for example, and we wonder these things all the time, right? What if Obama hadn't won the 2008 election? Would all these things that we've claimed are because of that have happened? What if 9/11 had never happened? What would the world look like today? To claim that Obama being elected caused X, Y, or Z, or that 9/11 caused X, Y, or Z, scientifically speaking, we in principle need to run these histories over and over and over and over and over again. Of course, as established, we cannot. You can do this with your own life. What if I'd never gone to college? What if I'd never moved to Tennessee? What if I never met Steve? Hypothetically. All right. So read more on counterfactuals. I'll put some notes below. Lots and lots of really interesting stuff on counterfactuals out there. All right. So when we're doing data science, we're almost always working in observational studies. Well, let me say, in this course, we're exclusively working in observational studies. And on average, when people refer to data science, they're mostly describing observational studies. So an observational study, unlike an experiment, is where some stuff happened in the world, we collect data on it, and we take a look. And we see what we see and apply the scientific method and see what we can do. Much of what we're going to work with is observational studies, meaning the researcher does not influence assignment to treatment or control. And this is a huge departure from all the scientific experiments that you've learned about, all the drug trials you hear about in the news, where the researcher explicitly influences treatment to control. I'm running a study on a drug. I randomly divide my research participants into two groups, and we'll talk about randomization separately, but we do it into two groups. And these 50 people get the drug and these 50 people do not. I influence the treatment and the control, drug, no drug. In the case that we see in the graph here of the relationship between cigarettes and lung cancer deaths, there is no researcher randomly assigning some people to smoke. If there were, we'd have a good experimental study. Some ethical problems, among other problems, with that. So we have this observational data. We don't want to throw it away. We feel like we can learn something from it, but we have to be cognizant of the limitations of this. And again, most data that we're working with or that we download from the internet or that our company hands us is observational. So in the case of smoking and lung cancer, as we see here, there's tons of observational data. It's pretty straightforward to write down how many cigarettes were smoked, or at least estimate how many packs of cigarettes were bought and inferences about smoking and so on, and to get, broadly speaking, records on lung cancer deaths. It's actually not a trivial exercise, but we have the data, and it's pretty widely available at this point. But we can't show causality that cigarettes cause lung cancer deaths from this graph alone, any more that we can dismiss that Nick Cage is causing drowning just because it sounds silly. This sounds compelling, so I'm tempted to say there's causality. That one sounded silly, so I'm tempted to dismiss it. But what if that one's right and this is spurious and we're totally missing something else that's going on that explains one or the other? As I said, there's big ethical problems with randomly assigning smoking, so we don't really have experimental data on that. As far as I know, if anyone's running that study, get in touch. I'll keep your secret. I would like to know. There are probably what's called natural experiments out there where randomly some communities have more cigarettes available than others, and you could probably tease something out. But generally speaking, we're working with observational data because these experiments are ethically difficult. If we have any reason to think cigarettes are bad for you, we shouldn't be randomly assigning them to people. There's also practical challenges. Handing out cigarettes to everyone in a city and not in another city is just kind of costly, expensive, time-consuming thing to do. And there's compliance. Just giving someone cigarettes doesn't mean they're going to smoke them all, right? Just like in drug studies, it can be a challenge with compliance where you say, okay, the treatment group is going to take the medication, but I don't know for sure that they took the medication when they got home. All right, so we've got observational data. Teeny tiny bit of terminology that will help us as we go forward, and is something that even if you never watch another video in this series or never do any data science, start describing the world in terms of independent and dependent variables and watch things become more clear when we argue about what might be going on in the world. It's very helpful vocabulary. Okay. So an independent variable, if we're looking at the world and we're saying, what's going on out here? What's causing this? How's that going to turn out? We're really talking about two types of variables. One is the independent variable. This is the factor we think causes the outcome we care about. So I'll make this concrete in a minute. We'll probably see independent variables referred to in the wild as IVs or just as X. And we'll get to that in the stats units in more detail. But the independent variable is the thing we think causes the outcome we care about. So it's the input that changes in an observational study or that we change in an experiment that we think affects the dependent variable. So it's in the case of cigarettes is X. We think X is going to cause the outcome I care about, lung cancer deaths. If I'm a doctor running an experiment, I'm giving out drugs. X is the drug, and the DV is recovery from the disease. The dependent variable is the outcome we care about, lung cancer, disease recovery. So the DV is affected by the IV. This is going to take a while to settle in your brain if you're anything like me, where you're going to like, which is which? Here's how to think about it. The DV, dependent variable, depends on the independent variables. The independent variables are just hanging out. I'm smoking or not for whatever reason, but has nothing to do with the study of lung cancer death. Lung cancer death, I am assuming, I am testing, I am wondering if it's caused by cigarette smoking, if it's dependent on cigarette smoking. It's a way to kind of remember it. We tend to use the language of treatment and control in experiments, and we tend to say DV and IV or DV, IV and control variables in observational studies. Control variables really are other independent variables we're not so interested in, but we'll get to that later. They're all the same thing, right? So our IV is our treatment, and our dependent variable or our outcome in our experiments or our observational studies are the same thing. So lots of different terms depending on the kind of research you're doing. We're going to say IV and DV quite a bit. And truly out there in the world, if you're arguing, oh, this is causing that, or you're wrong and I'm right, just take your argument and turn it into IVs and DVs, and you'll start to agree, realize where you really agree and where you disagree. Just a little tip for your internet arguments. All right. So putting it in the context of this example, so our theory, Smoking cigarettes causes lung cancer. Our DV, our dependent variable, the outcome variable, is lung cancer. That's the thing we think depends on the IV, which is cigarettes, smoking cigarettes. Here are some other examples. So if I have a theory that carbon emissions are causing climate change, say it with me. Our DV is climate change. Our IV is carbon emissions. Drinking too much coffee makes you feel fantastic. That is my theory by which I have lived my entire life. And in this case, my dependent variable is feeling fantastic, or how I feel. And my IV is drinking too much coffee or coffee consumption, perhaps. All right. So why is causality so hard? All right. We've established what it is. We've established DVs and IVs. Why is it so hard? So one big reason is something called deterministic versus probabilistic causality. So in deterministic causality, X causes Y every single time. Every single time you throw something up, gravity causes it to come back down. There's no sometimes, there's no part of the time, there's no on average. It's just what happens, right? Deterministic. This is very common in research done in physical sciences, so gravity. Another one, on the other hand, and one that we'll be living in more often than not, that's very common in the social sciences, is probabilistic. An increase in this makes people more likely to go vote, makes people more likely to get jobs, make people more likely to fight violently against one another. This is generally where we're living if we're doing anything to do with social data. And it can pose challenges for inference, because if we go back to testing hypotheses and we say, well, is it the case that X causes Y? And we see some evidence where X happened and Y didn't happen, we'd say, well, our theory is wrong. But maybe if we did that study 100 times, 90% of the time, we would see that relationship, and 10% of the time, we wouldn't. In principle, this could be because of measurement problems. Maybe we're just not measuring specifically enough, and so we're getting noisy measures. Generally speaking, we're going to talk about causal relationships in probabilistic ways. 3 signs we have causality afoot. Covariation, when X goes up, Y goes up. More smoking, more lung cancer. Temporal precedence, X happens before Y. First we have to smoke, then we have lung cancer. If we have lung cancer and then we're smoking, that challenges our causal ideas. And control for third variables. This is a big one. We need to make sure there isn't some third missing variable or confounding variable that's causing both X and Y. What I mean by this is Z is missing a variable. I'm trying to predict lung cancer. I have data on smoking, but maybe I'm missing another factor that really matters, such as working in a factory with toxic fumes. A confounding variable, and we'll say more about this in a moment, is something that affects both X and Y. So stress might cause people to smoke, and it might independently cause lung cancer, in which case we're going to get results that look like lung cancer is being caused by cigarette smoking when actually it's stress causing both. So these are some of the things we want to look for just to start to test the waters on causality. By the way, there are causal relationships where X can happen after Y, but they're rare. Happy to talk about that with you further in another video. Challenge 1 to causality. There are a few that we're going to do here, and then we'll wrap up. As I said, a confounder is something that influences both X and Y. So this graphic is a common example of confounders. You'll find it all over the internet, where we see, oh my gosh, there's an increase in rates of ice cream sales and shark attacks. And we might say, oh my God, we should never sell ice cream. It's causing shark attacks. Or if we want to sell ice cream, we should increase shark attacks. Maybe. But we're missing a confounding variable. In this case, it might be temperature. As the temperature goes up, people buy more ice cream and they also go swimming, therefore more shark attacks. So temperature is causing ice cream to go up and shark attacks to go up, therefore looking like they have something more meaningful linking them together. Challenge number 2 is reciprocal causality. This is where X and Y cause each other. This is an example of endogeneity. There are other ways that we can have endogeneity. I will probably be fast and loose with this and refer to this as endogeneity because I have bad habits. But so endogeneity, reciprocal causality, more specifically, is when we see a positive association between X and Y, but we can't tell if it's because X is causing Y or because Y is causing X. And it could be the case that actually both are causing each other. So for example, suppose we see a positive association between national political stability and national wealth. Well, it could be that a politically stable country is more likely to be wealthy, but it could also be the case that being wealthy can cause a country to be more politically stable. And it's probably both. And that makes it very difficult to do studies to untangle causality. And really, it lots of times depends on our knowledge of the area in order to make these claims. Some other examples of reciprocal causality: watching conservative news and having conservative political beliefs. There's a lot of talk in the United States and frankly around the world about, exposure to different types of media is causing particular political views. Could be, but it could be that having particular political views is causing us to consume particular types of media. Stress is thought to cause illness, but my goodness, illness can certainly cause stress. And getting grades in a course might influence how much you like that course. I have seen that among my students, but I have also observed that how much you like a course could be positively associated with the grade you ultimately get. So both can be true. It just makes it tricky to make inferences about causality. And too often I see people out in the world pick the causal direction that is consistent with their story and forget to consider that it could be going the other way. All right, last one. There are more, but last one for now is selection on the dependent variable. This is a very subtle one, and I see this ignored all the time. This is when we only consider, it's very tempting, we only consider cases where we see the outcome of interest. This is when we're trying to understand something. We look at cases where the thing we want to understand happened. So, for example, what causes war? Let's look at all the wars and see what they have in common. That's what a lot of us do, right? The problem with that is we have no way of knowing whether what they have in common is actually a cause or some other spurious things. All right, I'll give you some more examples in just a minute. So, in principle, what we need to do ideally to better understand causality is consider cases where there was not war. I need to see, okay, if I think disagreement over natural resources causes war, okay, but there are also many examples in the world where countries disagreed over natural resources and they did not have wars. So we would need to understand both those scenarios and the ones where war took place. So we end up with stories like, well, one cause of wars is being on Earth because all wars that we know of are on Earth. Earth causes war. When in fact, if we looked at cases where there wasn't a war, we would say, well, that's also on Earth. All right, let me get to more practical everyday examples. Oh, these are everywhere, everywhere. Recent study in the New York Times. I've interviewed 300 high achievers. First of all, what counts as a high achiever? About their morning routines. Here's what I've learned. They mostly boil down to getting up early, and as someone who likes to sleep late, the whole thing makes me upset. And the problem with this study is that what you need to evaluate to really understand what's causing high achievement is low achievers. Interview the losers, all right? That's what we need to do. Other studies, 12 secrets of people who've lived to 100. This gets into survivorship bias as well. If I want to understand what causes someone to live a long time and I only look at people who've lived a long time, I'll say, wow, look at these things they have in common. That must be what's causing them to live a long time, which tends to be things like have a gin every day. And it's like, you know what? I bet there are a lot of people who've had gin every day who didn't live a long time. You've got to look at the full picture. We tend to only look at half of the outcomes, right? What causes someone to recover from COVID? We need to study people who recovered from COVID and people who didn't. That becomes difficult, and that was a really depressing example, and I'm sorry for that. All right. On that cheerful note, we will end it. I will see you next time.